if you use MPI-IO for parallel I/O, you can set this environment variable, and it will tell you, it will produce a summary at the end of what was done on a file-by-file basis. If you decide to reorder ranks, we've not really talked about that, but this is what I was describing here, moving the ranks around to optimize the on-node communications, then you can ask it to tell you what the reordering was. You specify it in an mpitch rank reorder file, but you can ask it to report what it did based on that. And again, it should just match, but it's always a good sanity check. And finally, you can get information about the library printed out. So, you know, yes, this is extra information into the log of your job script, but there's really no reason not to set these. They're not going to have a performance implication because they either end up as, they basically are in MPI startup or MPI finalize, that they actually do anything. So that was MPI, a sort of overview of the Cray MPI, and that's all basically from a CPU perspective. Now, all of these things about protocols and so on carries over if you've got GPUs involved as well. So what I'm going to say is not, in terms of GPUs, is not something that's completely different to the CPUs. It's just some additional optimizations on top of all of this. So I guess that first of all, are there any questions on the CPU side of things? Yes? If you use the... Yes. Yep. Yes. Well, the cache that's specific to that core obviously can't be affected. I mean, the shared cache, yes, potentially. I mean, there could always be side effects, you know. So that's why you'd say you should experiment with and without it.
So the API knows how to import API address.
Yes. There is, I mean, well, I think now by default it will use the unused ones for the threads. There, in previous versions, pitch something use unassigned CPUs. If you do man MPI, and you look through there, you can find something about unassigned CPUs. So I believe that it's done by default now. Initially, you had to set this environment variable. I think it's set by default. But if you can always set it explicitly if you want to be sure. But that's when this mpitch env display is useful in your application to see that this was set or not. No, I mean, but on the send side, it's not really, I mean, on the send side, I don't think it's really a worry because, you know, you just like to send the data, and that's fine. I mean, well, you could, I mean, MPI single-sided is not as popular as, there are ways to do it. Think what you're talking about, I mean, what is more important is not relying on the receive side to do anything for the data to arrive. And then you are looking at what's called a single-sided communication model. It's not two-sided because the receive doesn't have to do anything. There is MPI single-sided, but the way MPI single-sided was written, certainly initially in the MPI standard, made it very hard to implement. But there are other single-sided models that you could use which interoperate with MPI. One of them is called SHMEM, one is Cray Fortran. And if you're interested in those things, so you can mix some of that into your application. You could convert your entire application if you wanted, but what typically people do is they have one particular place where it's very important that the receive side doesn't have to be involved. And in that, and if that kind of matches part of your application, then they put one of these single-sided communication models in, they replace the MPI, but only do it there. But that can be done, and we have had cases of codes where putting a bit of Cray Fortran into a Fortran MPI application did give performance speedups. Yes, I mean, yeah, the RDMA, the remote direct memory addressing, is where you can actually address the memory of a remote node with the Gemini. So, any more questions, or shall I move on to GPUs? So what I've been talking about basically up until now, I mean, I've given you some details, not because you especially need to know the details, but because it provides some insight as to why eager messages can overlap and rendezvous messages don't overlap and all these sorts of things. But these protocols and all these sorts of things are things that are generic to MPI, really. So if you have a different system with MPI, you will come across the same things. If it's a different MPI distribution, then the names of the variables may change and so on, if it's not MPitch. But what I'm going to talk about with the GPU stuff are optimizations that have been done with Cray MPitch. So the MPitch from Argonne with the Cray optimizations in it that are specific to the GPUs. Now, if you went away to some other GPU cluster that ran MPI, not all of this would necessarily work, what I'm going to talk about next. So if you really do worry about running on different systems, you've got two choices. One is you say, I will not take advantage of the optimizations when I run on Daint or Turdy. Yeah, both systems. Because I want to also be able to run on some InfiniBand cluster with some other MPI library. Or you're going to have to write your code in a way that it has the option to take advantage of this optimization when you run on a particular system. You will rebuild the code to take advantage of that. And in the practical that goes with this, we have a code that uses these optimizations, but can also be compiled in a way where it doesn't. So that's a template for how you might do it. So if you've got a GPU-accelerated code, again, the reason you're using Daint is because you've got a parallel. You're using multiple nodes, and every node has a GPU. So your problem data is sitting in the memory of a GPU, but that's only part of the global data for the problem. And you're going to need to do communications from one rank to another, but in this case, what that's going to mean is you're going to need to send data from one GPU to a GPU on a different node. So what could you do there? Well, the generic way, the way that will work everywhere, is that you say, OK, on the send side, I will first move the data from the GPU memory to the CPU memory. So I will call CUDA memcopy, if I'm using CUDA, for instance. I will then send the data over the network from the send CPU. It will be received over here on the receive CPU. And when it has been received by the CPU, it will be sent up to the GPU over the local PCI bus again. And that will work everywhere, because all of the MPI is happening on the CPU. There's no change. But this is inefficient, and it's inefficient because, first of all, the PCI transfers are quite slow between CPU and GPU. And this isn't anything special to Daint, it's just the fact that you're running on PCI 2 because that's what's supported for the Kepler cards. The other thing, and that's probably the biggest thing, is that the sender has to bring the data from its GPU, which I don't know why I always think about it. I always think about it up there somewhere. The data's got to come down, and at that point, the CPU has got to synchronize with the GPU to say the data has arrived. Then the MPI happens, and you do an MPI synchronization, and the data, now I know the MPI is completed, so I know the data has come over here, and then I will send the data from me back up to my receiving GPU, and then there'll be another CPU-GPU synchronization to say the data has arrived at the received GPU. So there's two local CPU-GPU synchronization points that have to go on. Now, what's the problem with that? Well, you know, if you use CUDA streams, you know that you can overlap data transfers, and of course you should be doing that. But the point is that whenever you do overlap stuff, what you want to overlap is a communication with something else. And, you know, if you have small children, the problem is they interrupt you every 2 minutes, so you never get anything done because you're dealing with the interruptions of, could you do this, could you do that, I can't do that, he won't let me do this. It's not that you don't get the time to do it, you just, your train of thought is being broken. Every time you have a synchronization point, it doesn't matter if that synchronization point doesn't take much time. If you want to get good overlap, the advantage of MPI, you know, is the idea that if you do it right, you've got all the time the message transfers to do some other computation, uninterrupted. If you've got extra synchronization points, you're going to have to somehow manage dealing with those synchronization points while you're doing this communication. So extra synchronization points just get in the way. And of course, there's also the potential that the data comes from the GPU into the CPU has a pinned memory buffer to do that. If it's not pinned, it should be. Then data is sent from the MPI library into the network controller. That will use a pinned memory buffer. If you don't do anything, these will be different pinned memory buffers. So you will also have a buffer-to-buffer copy within the CPU going on, because you've gone through the CPU. So the so-called G2G features in the Cray MPitch is a way of improving this efficiency. So what can you do? Well, first of all, in your code, you can call MPI, but wouldn't it be nice that instead of calling MPI as you did before, with data, send and receive buffers that are in the CPU memory, wouldn't it be nice if you could tell MPI, actually the data is on the GPU at this address in GPU memory, just get it from there. Why do I have to get it and do the synchronization with the GPU just to give you the data? So you can call MPI, but instead of passing in a buffer address that's in CPU memory, you can pass in a buffer address that's in GPU memory. So how do you know what that address is? If you're using CUDA, it's quite obvious because you'll have done a CUDA malloc, and that will have returned a pointer in GPU memory for that array. If you're using OpenACC, you can use something called the host data region to provide that address. And you can do the same at the receive side. So this is telling the MPI library where the data really comes from and where the data really goes. And obviously, if you provide that information, there's much more scope for the MPI library to optimize the transfers, because it knows the full path of the data, as opposed to you only telling it the CPU part of the path, and then adding on the GPU-CPU parts yourself. Is everything supported to do this? No. But most of the things that you probably want to do are enabled in the Cray MPitch. If you're doing something that isn't, you need to tell us, because we can add that to the implementation. It's being done on a request basis, essentially. So what are the changes in your code? Well, you need to call MPI, but with this device memory pointer instead of a host memory pointer. Host is the CPU, device is the GPU. For an OpenAC code, the code is still compilable to run on the CPU as before. As well as doing this in your CPU code, within your job script, you need to set 2 environment variables. This one must be set. If you don't set this one, your application will crash with a very weird error. You must set this. And then the other one that you set is this G2G pipeline, and I'll explain what that means in a sec. It's optional, but basically, if you use the zero, if you set it to be 0, which is it will use the system default that's 16. What are sensible values? 1 to 16. If you try and use a higher value, then it's not going to give you any benefits beyond 16. But you probably just want to set it to 0. You probably also, we talked before about setting this nemesis progress thread, setting these 2 environment variables. You probably want to enable that as well. It's not essential, but you will, if you don't do that, you're probably not going to see any benefits. So the data's got to move from one GPU to another GPU, and within the MPI library, once you've told it the full data path, you've told it it's going from this buffer in GPU memory to that buffer in GPU memory, then there are some optimizations that start to go on within the MPI library. So within the MPI library, the first thing that's done is that if the data moves through the CPU, you don't want to have one buffer to bring the data from the GPU and another buffer for MPI to talk to the network. You want to use the same buffer and avoid a buffer copy. So it will always use this what's called single copy method. You don't need to do anything, it just happens. And the other process it uses is called it's called pipelining, which I'll explain next. So I've got 3 stages to the process, potentially. The data is coming from the local GPU to the local CPU. Whilst that's happening, the PCI link here is busy, sending data across to the CPU. The network's doing nothing, and on the receive side, the PCI link over there is doing nothing because no data's been sent yet. Eventually, all the data arrives. Then I do the network transfer, and whilst the data is going across the network, the PCI links at both ends are empty. And then when the data finally arrives, it's sent up to the remote GPU, the network is idle, and the send side PCI bus is idle. Now, keeping the PCI bus between the CPU and the GPU, the slowest link in the chain. You do not want that to sit empty. You want to try and keep it busy because the bandwidth isn't great. So you want it running all the time if you can do it. So pipelining, what pipelining does is it splits the message buffer into smaller chunks. The first chunk comes from the sending GPU to the sending CPU. As soon as that chunk arrives, it's sent over the network. Whilst it's going over the network, the next chunk is coming from the send GPU, and then that moves over. So chunk by chunk, as each chunk arrives, it's sent off, and the next one comes across. On the receive side, as each chunk arrives, it's immediately sent up the PCI bus to the receive side GPU. So assuming that it takes the same amount of time, GPU, CPU, CPU, network, and then receive side CPU to GPU, if the 3 stages take the same time, they probably don't, but let's imagine they did. When the third chunk comes across on the send side and starts moving over the network, the third chunk is coming across, the second chunk is on the network, the first chunk is going back up to the receive side GPU. So you've got the 3-fold overlap going on. So obviously, it takes a little bit of time to get the pipeline up and running. It's going to take, if you've got 3 stages, it's going to take 3 cycles, 3 units to get it going fully. And it's going to, at the end, you'll have a few units where the pipeline is emptying. But in between, you're going to get good overlap. And this will increase the bandwidth. How many chunks should you use? Well, there are 3 stages in the pipeline, so if you don't use 3 chunks, you're wasting your time. But actually, because of the balance between the bandwidths of the different components, you probably want more stages. Internally, how does it work? Well, basically, it's using CUDA streams, if you know anything about CUDA, the asynchronous streams. It's using streams to queue up the PCI transfers at each end. More chunks, the more of these you've got queued, the faster it gets things through, just because there's less time getting the next one up and ready because it's all queued up. So more chunks gives you greater overlap. Of course, if the chunks get too small, then latency bandwidth trades off. But I would say just use 16. There's no point going more than 16 because you can only have 16 streams in the hardware. So it's a hardware limit. If you use less, there may be situations where it's less, but I think it probably isn't your major worry. So when are these used? Sorry. If you're working on TERDI with the Gemini network, all rendezvous path messages will go this way. So that's all the larger messages are done in this way. On the Aries network, it may or may not use the pipelining. Because the network is much faster, in some cases, because of the different network characteristics, it actually isn't quicker to split it into chunks. It may sound like it is, but it's not. And so there is a decision within the Aries network, within the silicon of the Aries network as to exactly how this goes. This is not something you go in and tune yourself. This isn't application dependent. This is just the characteristics of the network. It's been tuned by Cray. You don't worry about it. So that's essentially all I'm going to say in terms of the using MPI with GPUs. There's not really a lot to say. The optimization is to use this G2G stuff. And then perhaps, you might try playing around with number of chunks in the pipeline and that sort of stuff. But it will improve the bandwidth to do this. The time it takes to get from one GPU to the other. It does improve that bandwidth. But because of the PCI links between CPU and GPU, the bandwidth is not as great as CPU to CPU. It never will be. There's a hardware limit there. But, the data has to move from one GPU to the other, so you've got no choice because your code is running on the GPU. The real advantage to using this G2G as I see it is the fact that I've just told MPI the data is on my send GPU. It should move to the remote GPU. There's only one synchronization. When I call MPI wait all to synchronize the MPI to finish the messages, at that point, I know the data is on the remote GPU. I haven't had to do any synchronizations between the send CPU and the send GPU or the remote CPU and the remote GPU. I've avoided those two extra synchronizations so that, yes, it's going to take me time to transfer the data, but I've got much greater scope for overlapping that with some independent computation. Now, of course, if you've got nothing to overlap it with, there you go. The G2G will still give you a bit better bandwidth. But the secret to GPU programming is, a GPU, as we'll see, is a very asynchronous beast. Everything is done asynchronously. And if you can't take advantage of that, you send something off to the CPU and then or you initiate a data transfer and then you're free to do something else. If you can't take advantage in your code, you will be limited in the performance that you can get out of the system. And that's just true. It's not that's the way GPUs work. So are there any questions? Yes? It should just match, but it's always a good sanity check. And finally, you can get information about the library printed out. So, yes, this is extra information into the log of your job script, but there's really no reason not to set these. They're not going to have a performance implication because they either end up they basically are in MPI startup or MPI finalize, that they actually do anything. So that was MPI, a sort of overview of the Cray MPI, and that's all basically from a CPU perspective. Now, all of these things about protocols and so on carries over if you've got GPUs involved as well. There is, I think now by default, it will use the unused ones for the threads. They're in previous versions, pitch something use unassigned CPUs. If you do man MPI, and you look through there, you can find something about unassigned CPUs. So I believe that it's done by default now. Initially, you had to set this environment variable. I think it's set by default. But if you can always set it explicitly if you want to be sure. But that's when this mpitch env display is useful in your application to see that this. So what I'm going to say is not, in terms of GPUs, is not something that's completely different to the CPUs. It's just some additional optimizations on top of all of this. So I guess that first of all, are there any questions on the CPU side of things? Yes? If you use the yes. Yep. Yes. Well, the cache that's specific to that core obviously can't be affected. I mean, the shared cache, yes, potentially. I mean, there could always be side effects, you know. So that's why you'd say you should experiment with and without it.
So the Iran knows how to change support in MPI threads.
Yeah, if you use MPI I/O for parallel I/O, you can set this environment variable, and it will tell you, it will produce a summary at the end of what was done on a file-by-file basis. If you decide to reorder ranks, we've not really talked about that, but this is what I was describing here, moving the ranks around to optimize the on-node communications, then you can ask it to tell you what the reordering was. You specify it in an mpitch rank reorder file, but you can ask it to report what it did based on that. And again,